Okay, so we are now ready to talk about the fundamental subspaces of a matrix. That should be a plural there. Fundamental subspaces of a matrix. So we have a general m by n matrix here in its general form using our double subscript notation. If you remember, in this case, the first number corresponds to row, second to the column number. Rows go row 1 at top, row 2, and so on. Notice we have m rows and n columns. Now the row vectors of A, right, are, notice, n tuples, right? Because each row is how long? It's n long because there's n columns. So they're n tuples, and they can be written this way, right? All right, in this form here. These are the m row vectors of the matrix A. In a similar way, the column vectors of A, right, are m tuples because there's m rows, right? I listed them down this way. So we have n column vectors that are all m tuples for the matrix A. Okay, so with that, breaking down the rows and columns of A, we're now ready to talk about three subspaces associated with any m by n matrix. The first is the row space of A. My notation for the row space of A, sometimes I'll do this shorthand, row of A. It's the span of the rows of the matrix of A. It's the span of the rows. If you remember the very beginning, when we talked about subspaces, we proved that the span of any set of vectors forms a subspace of the corresponding vector space. The column space of A, I denote sometimes this way, is the span of the columns of the matrix A. And then the null space of A is the third subspace we're going to talk about, which I denote sometimes this way. This is the solution space of AX equals 0. Okay, so we have talked about this. In fact, in the last two videos, technically, we have talked about the solution space to AX equals 0. In fact, we found a basis for in the dimension of an example of the solution space of AX equals 0. This is also the kernel of the matrix transformation whose standard matrix is A. So three ways of talking about this. The solution space to AX equals 0 is the kernel of the matrix transformation whose standard matrix is A, and it's the null space of the matrix A. And we'll talk more about this relationship here in the next set of lectures. Okay, so now I want you to tell me, we know that each one of these row space, column space, and null space are subspaces, but of what space? The row space of A is a subspace of what? I'm going to give you a little hint. You just need to tell me what the superscript is. What space is it? Well, what objects reside in the row space? The row space is the span of these m row vectors of A. Right? So any object in the row space of A is a linear combination of these m row vectors. And look at the row vectors. What are they? Where do they reside? They reside in n space. They are n tuples, right? Because that's the number of columns. That's how long they are. They are n tuples. So any linear combination of these row vectors must be an n tuple. Therefore, it resides in n space, and therefore the row space is a subspace of n space. What about the column space? Where it's a subspace of what vector space? Well, any vector in the column space of A is a linear combination of the columns of A. What type of objects are the columns of A? They are m tuples. They reside in m space. So the column space is a subspace of m space. What about the null space of a matrix? Well, the null space is the solution space to AX equals 0. Remember, A is what size? M by n. So what are we talking about for X? What does it have to be? What size matrix? N by 1. it's what? An n tuple, right? It's an n tuple, so it resides in n space. So notice the row space and null space are subspaces of n space, but column space is a subspace of m space. Okay. So we're going to talk a little bit more about these new subspaces. In fact, we will shortly be talking about what is a basis for and the dimension of each one of these things given a particular matrix A. So we're going to tackle that question. But I want to talk a little bit about just the concept of column space in particular. We have already kind of talked about this, but here is an important theorem. A system of linear equations Ax equal b is consistent if and only if B, the constant matrix, is in the column space of A. And really the proof, I'm not going to prove it, but I'm just going to give you an example, something we've talked about before. When we talk about the product A times X, the matrix A times the vector X, you can think of that as a linear combination of vectors, and those vectors are the columns of A, and the coefficients come from the matrix X. I'm just going to illustrate this, right? In this example, I want to take a look at the system AX equal B, right? And what would that look like? If I do A times X, what's that going to look like? This is a 2 by 3 matrix here, and X is 3 by 1, so we're going to be able to multiply, right? First row dotted with the column, right? Take the dot product. What do we get? 6x1 plus 1x2 plus 3x3, right? And then this row dotted with this column gives us our second row, 2x1 plus 5x2 plus 4x3. All right, so there's our 2 by 1. All right, we get a 2 by 1 matrix. And there's our two equations. You can see them, right? The first equation is 6x1 plus x2 plus 3x3 equals b1, and then the second equation. So there's our system of linear equations, sort of in matrix form. But this matrix product here, right, A times X, right, can also be thought of as a linear combination of the columns of the matrix A. And let me show you how to do this, right? You'll see the common x1 here and here. What I'm going to do is do x1 times the column vector 6, 2 plus x2 times the column vector 1, 5 plus x3 times the column vector 3, 4 equals b1, b2. Right? So this is the same information, right? But now this matrix product AX, right, is written what? As a linear combination, right? The coefficients are x1, x2, and x3, which are the unknowns, right, from our variable x, the variable matrix there. And then the actual vectors, right, are here. And notice these vectors, where are they? 6, 2, that's the first column of A, 1, 5 is the second column, and 3, 4 is the third column. So what do we have here? We have a linear combination of the columns of the matrix of A. Well, by definition, this resides in what? The column space of A. That's the column. That's what we just talked about. The column space of A is the set of all vectors that are linear combinations of the columns of the matrix A. So I have here a vector in the column space of A, and it is equal to what? The vector B, right? So B is in the column space of A because B can be written as a linear combination of the columns of A. And how do we know it can be written? Because you say, well, x1, x2, and x3, what are they? Well, we know there exists at least one set of x1, x2, and x3 that works because why? We said this system is consistent, meaning there's at least one solution. Right? There's at least one solution. So there may be exactly one or there may be infinitely many, but we will always be able to write B as a linear combination of the columns of A. So the system AX equal B is consistent if and only if B is in the column space of A. So I didn't really prove it in general, but that sort of illustrates the way that would work. Okay. One more thing then connected to this theorem. So if a system of equations AX equal B is consistent, well, if that's true, That's going to be true if and only if what? B is in the column space of A. So if this system is consistent, B is in the column space of A. If B is in the column space of A, then the system is consistent. Now, if A is m by n, and m is greater than n, so the number of rows is greater than the number of columns, then AX equal B is inconsistent for at least one B in M space. So if M is greater than N, here we have a system of linear equations, right? And what is it? M is what? The number of equations. N is the number of unknowns. So if M is greater than N, then we're saying we have more equations than unknowns. Such a system is sometimes called overdetermined. If we have fewer equations than unknowns, then that's usually called an underdetermined system. Okay, so this is overdetermined. And notice B is in M space because why? A is m by n, again. And x is n by 1, and therefore the product AX is what? M by 1. So B is m by 1. And what it's saying is, if we have more equations than unknowns, then this system is going to be inconsistent for at least one such set of constants. Okay, it may be consistent for some, but there's at least one B in M space where the system would be inconsistent. Okay, and so this is an important thing to talk about when we talk about systems that are underdetermined or overdetermined. Being able to talk about whether the system is inconsistent or consistent is important. And so this is a nice little thing we can prove, and pretty clear here. Let's see, the matrix A has n columns, right? A is m by n, it has n columns, and those columns are what? M tuples. All right, we talked about that, right? Because the number of rows is m, for each column is m long, if you will. It's an m tuple. All right, each column is an m tuple because there's m rows in the matrix A. Since we know that m is greater than n, or what? N is less than m, so I'm just doing that in the mirror image, if you will. N must be less than m if m is greater than n. Since n is less than m, these, I'm going to need a comma there. Since that's true, these n columns cannot span M space. Now why is that? Why can these columns not span M space? We'll go back to when we were talking about dimension. Go back to the dimension video. We talked about the fact that if you have fewer than your dimension vectors in a set, they cannot span the space. If you have fewer than your dimension vectors in a set, they cannot span the space. What is the dimension of M space? The dimension of M space is M. How many vectors do we have? We're talking about columns, right? We have n columns, n column vectors. They're m tuples, right? They're in M space. They reside in M space. M space is dimension M. We have n vectors that we're talking about, n columns. N is less than m. We have fewer than the dimension vectors, therefore those columns cannot span all of M space. And what's that mean? Hence, there is at least one vector B in M space such that B is not in the column space of A. All right? Well, how can I say that? Well, because these n columns, right, any vector in the column space of A is a linear combination of these n column vectors of A. Right? And we just said these n column vectors cannot span all of M space. What's that mean? It means there's at least one vector in M space that I can't write as a linear combination of those columns. There's at least one, right? And so that means that there's at least one B that is not in the column space of A. But what's that mean? By the previous theorem, what was that previous theorem? Let's just remind ourselves, right? System of linear equations is consistent what? If and only if B, the constants vector here, is in the column space of A. And so, since B is not in the column space of A, then the system AX equal B for that at least the one B must be inconsistent. So by the previous theorem, there is at least one B in M space such that the system AX equal B is inconsistent. And there's the proof of that. Okay, so there are some certain things we can talk about in terms of using the language of the column space of A as we did in this theorem, and also the null space and row space, and we'll look at some of those things. But in the next video, what we're going to look at then is continue this idea of these fundamental subspaces of a matrix, and I want to find a basis for and the dimension of each one. I want to find a basis for and dimension for the row space, column space, and the null space. We actually already did the null space. We will do it again, but the row space and column space will be new, so we'll do that in the next video.